Hello everyone, so today we're going to cover the estimation of frequency-based rainfall using FARD 2006. So what is frequency-based rainfall? So frequency-based rainfall refers to statistical rainfall estimates derived from historical rainfall records. The process involves extracting the annual maximum rainfall, AMR, for different durations. For example, 1 hour, 6 hours, 12 hours, 24 hours, and so on. And then fitting this maxima, or AMR, to a probability distribution is the next step. Commonly, this is the Gumbel distribution in case of Korea. And then estimating rainfall depths corresponding to different return periods, for example, 10 years, 50 years, 100 years, storms, is the last step. This produces rainfall estimates that are not just observed, but statistically representative of rare extreme events that are essential for flood risk management and design. So first, we have the input data, 69 weather stations of Korea. So rainfall data are collected from 69 long-term meteorological stations across Korea. These stations provide time series rainfall data, hourly or daily, ensuring enough records for extreme value analysis. Each station represents a point measurement, so further special interpolation is needed to produce regional rainfall estimates. Which brings us to the Spatial Interpolation National TSIN network. So to extend point rainfall values to regions, Korea applies the TSIN polygon method. The country is divided into polygons around each station. Rainfall at each station is assumed to represent the entire polygon area. This ensures that each part of the country is assigned rainfall values based on its nearest gauge, correcting for uneven station distribution. So the TSIN polygon method is a spatial interpolation technique used to estimate average rainfall or any point-based data over an area. It divides a region into polygons around each measurement station so that any point inside a polygon is assumed to be best represented by the station located at its center. As you can see in this image, each red dot is the symbol for rainfall station. So how it works. So start with rainfall stations plotted on the map. So in this case, it will be A, B, C, D, E, F. And then connect all the neighboring stations with straight lines, or in this case, dotted lines. And then draw perpendicular bisectors of those lines, and these lines will divide the space into polygons. So each polygon is associated with one station. The rainfall value from that station is assumed to apply uniformly across its polygon area. So in this case, the rainfall station A and the polygon that is associated with it will have the rainfall value from that station. So the formula for calculating area average rainfall is P equals summation of A times P over summation of A. So if there are n stations, the equation is as shown here. So P equals average rainfall over the whole basin or region, and A sub I is equal to area of polygon assigned to station I. And P sub I is equal to rainfall observed at station I. So the output is frequency-based rainfall maps for 161 cities and counties. So using FARD 2006, frequency analysis results, for example, 50-year, 24-hour rainfall, are mapped across 161 administrative regions. So the map shows the red zones, the ones with the high values, show northern and eastern part of Korea, where extreme rainfall is higher due to orographic and climatic effects. So the green zones, or ones with the lower values, show southern and western regions where probability rainfall is relatively smaller. This map is used as the basis for design rainfall input in hydrologic models and flood design standards. So let's talk about collection of rainfall data. So first, we have to download the rainfall data in time units from the Korea Meteorological Administration (KMA's) weather data opening portal. And And then we have to choose if we're going to use ASOS or AWS data. In this exercise, we'll calculate the frequency-based rainfall using 30-year rainfall data from 1989 to 2018 from the ASOS Seoul number 108 station. If there is a missing value not available in the downloaded rainfall data, it should be corrected to 0. So estimation of annual maximum rainfall by duration. So why estimate annual maximum rainfall by duration? To use the concept of critical duration when calculating the flood discharge. Critical duration is the rainfall duration that produces the maximum flood discharge or peak flow for a given watershed. In other words, if you simulate floods using different rainfall durations, 1 hour, 3 hours, 6 hours, 12 hours, and so on, the critical duration is the one that yields the highest peak discharge at the watershed outlet. Suppose a watershed is analyzed using frequency-based design rainfall of different durations. So 3-hour rainfall with a peak discharge of 220 cubic meters per second. 6-hour rainfall with peak discharge of 280 cubic meters per second. And 12-hour rainfall with peak discharge of 260 cubic meters per second. The critical duration will be 6 hours because it produced the maximum peak discharge of 280 cubic meters per second. The annual maximum rainfall is usually calculated by using coding programs such as Python and R, or an Excel spreadsheet. In this exercise, we'll use Excel to calculate the annual maximum rainfall for each duration, 6 hours and 12 hours, of ASOS Seoul number 108 station for 30 years, from 1989 to 2018. In terms of hydrology, rainfall for each duration refers to rainfall during random time, not during a fixed time. Rainfall data from the KMA are fixed time data. Therefore, we should apply the conversion factor to fixed time annual maximum rainfall to convert to the random time annual maximum rainfall. So as you can see in the table below, we have a table for fixed time, random time, and conversion factor. And then we have the regression curve of fixed time and random time conversion factor. So for our case, since we're using 6 hours and 12 hours, we'll multiply our 6 hours with 1.012 to convert it to random time annual maximum rainfall. And for 12 hours, we'll multiply it by 1.005 to convert it to random time annual maximum rainfall. So let's talk about FARD, or Frequency Analysis of Rainfall Data, 2006. So it's a program that calculates the frequency-based rainfall by analyzing the frequency of rainfall data. And as you can see, there's a link down below that you can click on and follow into this website where you can download the zip file version of FARD. So when you open FARD 2006, this is how it looks like, and you should pay attention to a table of contents on the left side, as you can see in the red rectangle in the picture here. So this is what it says in the table of contents in Korean translated into English. So the process is carried out in the following order. So first you have to click on Data Input, and then Data Analysis, View Results, and Save Results. So that's how the process goes, and the meaning of what it is in Korean into English is as shown in the pictures below. So in Korea, the estimation of frequency-based rainfall is currently performed using the method of frequency-based weighted moments for parameter estimation, with the distribution most commonly represented by the Gumbel distribution. So as you can see in the picture below, we have multiple options. We will select all of them, but we'll mostly focus on looking at method of probability weighted moments in the results option. So once data interpretation within the data analysis is completed, the results are automatically saved in the same folder as the input data, basically as the same as where you have your data. So to start using the FARD, fill in the FARD input form in Excel file with the calculated annual maximum rainfall for each duration. And when you do this, do not change anything that's already in the FARD input form. just fill in the numbers that you got using Excel spreadsheet earlier. So caution, FARD input value cannot be read by FARD 2006 if the FARD input form is written in CSV file. Therefore, FARD input form must be saved in the Excel 97 to 2003 workbook format to be correctly recognized by FARD 2006. So once you have saved the FARD input form into Excel file, you'll be able to open it within the FARD program. As you can see, my mouse cursor moving. So this is where it says open your Excel file. So you click on this button where my mouse cursor is moving right now, and then you'll be able to upload the numbers directly into this interface. And after you do that, you will go to subject of analysis, which is this box right here where you can click on it and then type in 108 for your rainfall station number. And then you can go to the right and see the start year, and this is where you can start, and this is where you can choose your start year. And in this case, we'll change the start year to 1989 because that's when the data starts. And when you choose that, this table will start with 1989 instead of 1997 that's shown right now. And you'll be able to change all the years, and the data will stay the same, but the years you have to change them by using the start year button and then selecting the correct start year. So run test, turning point test, preliminary analysis. So the tests that confirm the randomness of the input data. And then we have goodness of fit test to test whether the frequency-based distribution drawn when estimating parameters from the input data fits well within the error range. So we go to view results, frequency-based water quantity estimation, and you can check the frequency-based rainfall by return period and duration. So when we open up the results section, we'll be able to see the method of parameter estimation. And if you go to this section where you can click on this triangular button and then choose a different method of parameter estimation. In our case, we're interested in method of probability weighted moments. So you need to click this and make sure you choose this one. As for the duration, as shown in the previous slide, you don't have the option to change the duration as it's just shown in 360 and 720. But as we know, this one is 360 is 6 hours, and then 720 is supposed to be 12 hours. So if you go to this triangle button again, where it says duration, then if you click on the triangle, you can choose between 360 or 720, or in our case, 6 hours or 12 hours. And then now, once we have the results, we're interested in looking at the Gumbel distribution because that's the most commonly used probability distribution that is used in Korea. So if you look at this Gumbel distribution as shown in this red box, we see that it says GUM on the top, and then you can see the return periods on the left side, and they are in terms of units of years. So 2 years, 3 years, 5 years. And then if you go 2 years, go across, stop where it says GUM. So for the Gumbel distribution of 2 years return period, the frequency-based rainfall is 110.1. So the result of the frequency-based rainfall can be found in results folder or FARD quantile.dat among the files created during data analysis, data interpretation part of the workflow. So if Notepad is set as the associated program, the results can be opened directly in Notepad. So basically go to a folder that says result, and then you can open FARD quantile with using the program Notepad. So save results, save as a file. So that option is where you can save the results as a file up to the stage completed in the current work. So if you go to FARD quantile part of your results folder, then if you use Notepad, then you can open it up like this, and then it will show you all different kinds of distribution, and then you'll be able to see all the results in the form of Notepad like this. So if you look into the red box, it says distribution, GUM, and then you can see all the return periods, 2, 3, 5 years, and so on. And then we have 360, which is 6 hours in our case, 110.1, 132.0, and so on. And then 720, which should be 12 hours in our case, 144.5, 172.6, and so on. And then these two other pictures are graphs they can see in the FARD program. And that is the end of our slides, and that is our end of our lecture. And next, I'll show you the whole process of how to do this. Thank you.